Welcome back, dear participants. So it is my immense pleasure to introduce our next resource person, Dr. Anwesha Khasnobish, who is an accomplished scientist with a PhD in biomedical engineering from Jadavpur University, Kolkata, and completed in 2015. She further honed her expertise during her postdoctoral research at the prestigious DFH chair in Brain Machine Interface Lab at EPFL, Switzerland, supported by the Swiss Government Excellence Fellowship in 2017-18. Currently serving as a scientist at TCS Research, Kolkata, Dr. Khasnobish specializes in cutting-edge technologies, including physiological sensing, bioinstrumentation, brain-computer interfaces, haptics, sensors, embedded systems, and biosignal and image processing. Her recent work focuses on leveraging microwave and millimeter wave technologies for human sensing and monitoring applications. I wish that this session is going to be a very engaging and insightful, and we are very much delighted and excited to hear from you, Dr. Anwesha. Over to you.
Thank you, Dr. Shah. Thank you for having me here. Good evening, everyone. I'll just share my screen. Um, is my screen visible to everyone?
Yes, yes, sure.
And
Yes, ma'am.
okay, thank you. And I hope that I am audible.
Yes,
Um,
Dr. Anwesha, you're very much audible.
Thank you,
Please
ma'am.
go
So
ahead.
I'll just start. Good evening, everyone. So as Dr. Shah mentioned that today I'll be talking about uh, the research of not my research, I would say, but the research of my team on unobtrusive health, smart health monitoring that we have done for past some years now at TCS Research, Kolkata, specifically at Kolkata. Um, before going to before going into the technical details of my talk, just I'd like to give a very brief idea of you about from where I belong. So I belong at TCS Research. Um, I just want to mention in the very beginning, as Professor Shah has already mentioned, that I am a biomedical engineer by background and by from my academics, but I belong to this thesis research where I work specifically on biomedical signal processing, instrumentation, and imaging. So at TCS Research, we have different areas and groups. So we mainly the foundational research that revolves around these four pillars, that is life sciences, physical sciences, mathematical sciences, and behavioral sciences. So these are the four pillars of the foundational research on which TCS Research has lays its foundations on. We have a ecosystem which helps us to do the research and then implement it over the practical life scenarios in which we have uh, collaboration between academia, startups, accelerator VCs, and also alliance partners. In our innovation, we have a joint effort from where we consider industry, society, markets, and digital technologies. So we have different research areas at TCS Research. So like embedded devices, deep learning. So we have a lot of different research areas. The research area from which I belong it is specifically known as embedded devices and intelligent systems. So in this research area, my team is specifically called unobtrusive sensing. So why unobtrusive? So first, I'd like to tell you whatever research we do, we application wise, we try to categorize it in two different broad categories. One is for human sensing and another is for machine sensing. So whether it is for human sensing or for machine, what we are doing is sensing from a distance or sensing in a non-contact way. So we use different methods of non-contact sensing, be it RF, optical, acoustic, thermal, hybrid, or whatsoever it is, sometimes multi-sensor fusion also. So we have novel imaging and signal processing algorithms that we build on, then we have our sensor fusion backbone, and upon that we what we do is using these different types of sensing methods or sensing physical technology methods. What we are trying to measure are these physical quantities or material properties, either physical quantities or material properties. And then at the final interface, we have our own edge system, which we have developed for our sensing systems or sensing solutions, what we call them as sensing solutions. Now I'll just start with what I wanted to discuss with you today. Um, so this particular picture, so I'll just take a pointer. Just so this particular picture, and then coming to these parameters, that sleep, fat, mass, steps, does it ring a bell to you? Like, do you find this particular slide anything relatable? I don't know whether you can unmute your mics. If you can, then please like feel free to answer. Let us have an interactive session rather than just only me speaking. So uh, I'd like to just go on with this again. So this particular picture, like I think now most of us are very like used to this particular device that a lot of us use on a daily basis, right? So this is just like wearable or smartwatch. Um, Now, this is a little bit old statistics about the wearable users in India by age. So, what you see in this histogram, it shows that the maximum number of users, if we distribute by age, falls in the age group of 25 to 34, and the least number of users, if we categorize by age, is like 55 and above, or it might be 60 and above. So now my next, but at the same time, what you see is this is a graph that is showing the expanse or the growth of wearable market throughout the world. So, and you see, so this is a prediction of the wearable market expected to grow by this much amount in 2031. So you see, this is a very steep growth, but that growth is like limited to this specific use group to be very specifically. Now, another data that also shows that the world is aging, right? With the development of medical technologies, with the advancement of medical technology, the advancement of healthcare, the advancement of our state of living, uh, the world is aging because now the expected lifespan has increased. So we have a lot of senior citizen population that is living with us, right? Uh, Now, here another question that I'd like to uh, like I would like you all of you to just think for a moment. Like we all use like the smartphones or smartwatches or some devices on a daily basis, like some or the other. But how many of you have how many of your parents or the other older members of your family have you seen using this let's say to be very specific, the smartwatches? At least none of my parents or parent-in-laws in my house does that. So even I find it very difficult to get them use the technology, though they are using it for some time now. So this is a practical challenge. Now, these elder generation or this elder population, what do they need? So this elder population is at a very high risk. So they sometimes live separated from their families. They have some physical disabilities, and they are like, due to age, they have some age related problems and all. But like, so to have a quality of life, we need to monitor these particular activities of these people. So before going to this particular thing, let me just tell you a small story how we began this research. So there is a facility in Singapore. So where so you can think of that facility as an apartment. So there's a society in which there are apartments. The apartments are either 1 BHK apartment or 2 BHK apartment. In that, uh, like it is specifically for senior citizens or elderly people living there. So either a person is living alone or a couple is living, like husband, wife, or something like that. So and they have, as because that is a senior citizen facility or a facility that is run for the elderly people. So they have dedicated doctors, nurses, medical facility, ambulance, and all other things. But what the management or the doctors or the caregivers of that facility was finding difficult is to monitor the health of the residents of that society on a regular basis or on a day-to-day basis. Because first of all, you cannot track them uh, with a camera, right? Because that is absolutely we none of us would want like cameras to be put in our inside our homes. So the same thing was with them. They did not want cameras. Again, there was the issue of privacy. So camera is out of question for monitoring them. Now, another like there are a lot of different like gadgets that can be worn on the body. But again, these population or these people were really finding it difficult to like allow the caregivers to wear the technologies on a regular basis. And also like coming the caregivers coming in and then monitoring their like vital parameters every day or every hour was also not a feasible work. So they needed something, some technology or some solution which could like continuously monitor the health of the patients or health of the residents, right? So the need was to monitor fall detection, activity, localization, and vitals. So why fall detection? Because the elders, are very prone to fall. So due to some or other reason, if they fall or they are very prone to fall, and if they fall, that can even be fatal. And so and also they needed to localize where they are, like localization where a particular person is currently or how the person was behaving throughout the day in a 24/7 basis, what activity he or she has performed, and also the vitals. So their vitals means, let's say, for your heart rate, respiration, sometimes a temperature, BP, all these things comes under vitals. So we needed a monitoring of liveliness, or we called it liveliness monitoring. So, so we needed to monitor these parameters, but at the same time, whatever solution uh, that we come up with should be secure, non-intrusive, easy to use, and effective. So secure, obviously secure in terms of data, secure in terms of privacy, non-intrusive because none of the solution should interfere or intervene with the daily lifestyle of the residents. So that should not happen. And obviously it should be easy to use, because otherwise nobody would like to use it. Or if that the usage of that particular technology, if that required like very technical intervention, it would be very difficult to implement it to a lot of people or a large number of people. So what we intend to do is we want to monitor the liveliness. So let's say, so this was the actual floor plan of one of those facilities. So let's say there are two bedrooms, one like living room and all those things. So we need to monitor the liveliness of the person. So that should be invisible, non-intrusive, and monitoring 24/7. So 24/7 monitoring was also another challenge and the need of the hour for them. So what we proposed, our proposition was electromagnetic waves. So uh, just think what comes to your mind when you hear the words electromagnetic waves for these type of applications, right? So to be very specific, the radars, right? But isn't the radars huge, like really huge? So let me tell you my perspective. As I myself belong from a non-microwave, non-electronic background, so for me, the only thing that came to my mind when I heard or hear the word radar was these big radars that we can see in and around the airports or maybe in some TVs and movies. But like thanks to Moore's law, now we have a different variety of radars that are easily available on the market. So now, let me be specific. Now, if the question might arise that have we built these different types of radars, or do we build radars at TCS Research? So my so I would like to give you a clarity is that we don't build radars, right? Whatever radars you are seeing here, let's say this is one radar, this is another type of radar, this is another type of radar, and this is another. So all these different types of radars that you see here that we have not built. So we buy off the shelf radars, but what we build is that the technology or the solution in and around it. So we have different, so we have the solution, these we have different solutions which we have already patented. So now the solution that we give to the Singapore community of who came to us, and the community was called Shine Senior. To the Science Senior, we gave them the solution which is called the LISENS. So LISENS, we define it as life sign sensing. So what do we mean by life sign? In life sign, we specifically it consists of cardiopulmonary signals. The cardiopulmonary signals, I mean, cardio means the related to heart, and pulmonary means related to like lungs or respiration. So the respiration signals or the respiration monitoring and the heart beats or the heart rate monitoring. And the other thing was the activity monitoring. So let's say uh, whatever solution we are building should be able to detect in a broad category these parameters or these physiological signals. One is respiration, the another is heartbeat, and the other broad category is activity, gesture, or gait. So just think about this picture for a while. Some of you, I'm sure, know that what this person is going through or why this person is attached to so many wears or like wears and strings to this person, like what is being done to this person. Just give it a thought for a couple of seconds. So if you see this picture for a very first time, some of you might think that this person might be a patient, this person might be lying in a hospital ICU or in a very like emergency condition, so that a lot of wears are coming out of his body and a lot of parameters are being monitored. But let me tell you, this is how sleep monitoring is done. So polysomnogram is done, sleep monitoring or polysomnogram is done by attaching so many sensors on the body, right? Now just think about if you are being subjected to so many sensors which are attached to your body through so many wears and tapes, would you be able to sleep? Forget about the sleep study. So this person is being subjected to sleep study with so many sensors and like wears here and there. So what we needed is there should not be any strings or what we call as invisible sensing. So as I was mentioning, we proposed this idea of radar based or electromagnetic waves based vital sign or life sign sensing, where the sensing is completely invisible, or we call it the power of invisibles, where there will be no sensors or strings attached to the body. So this is the bird eye view of our whole solution. So what we are trying to do is, so first of all, let's say I put my sensors or the radars in a particular room. So let's say this is the room where I want to monitor the person, or like monitor or detect the liveliness. So the first thing I would like to detect is the presence. So first thing we would like to see if there is somebody present in the room, somebody with some human, if there is some human present in the room. If there is some human present, then we would like to see whether that person is moving or not. Let's say, so what I said previously is that now we are calling it life sign sensing or liveliness monitoring. So we are trying to detect whether a person is alive or not. Why? Let me again go back to my words a few moments back. So what we were intending, so our solution was intended for the people living in a society, uh, in some like apartment, where we wanted to see or monitor the health of a person. In
Yeah.
that, the first thing that the first or the most important thing that we needed to monitor is the fall detection, or whether the person is alive or not. So if a person is moving, so if a person is walking, moving, doing some stuff, doing some activities, maybe eating, or maybe doing a phone call, sitting somewhere, so that means if the person is moving, that means that that person is alive, right? So if the person is moving, uh, then we detect the or we categorize that activity or movement. That can be walking, sitting, eating, finger movement, tossing or turning in bed, whatever it is. But if the person is stationary, that means the person is almost at rest. So that might happen. Let's say if somebody is just sitting on a chair, relaxing and reading a book, in that state also the person is almost stationary. Other times it might happen that the person is just sleeping. So that time also the person is stationary, but obviously not unconscious. So there's a difference between the person being unconscious, not alive, and like just stationary. So if the person is at rest or stationary, then we detect the cardiopulmonary signals. So in that cardiopulmonary activity, we monitor the respiration and the heartbeats. So this is what we are trying to do, or this is what we try to do. So, going into a little, so as I told, so the things were cardiopulmonary health, gestures, fall detection, or the rehab progress. So these were the applications that we were focusing on. So, we had different like modules of your solution. I'll come to that later. So I'll just show you a very small video. So this is just our lab setup, one of our lab setups. So and if you see, this is a person standing, and here this very small white box, this is our radar, and you might see that there is nothing on the body, there is nothing attached on the body, there is no strings. So the person here does some activity. So here the person does some, I'll just, yeah, does some activity, and you'll see that we are detecting the activity here. So as I told, so one of the objectives of this solution was like if the person is not stationary or moving, then we would like to know what activity that person is performing. Right now, let's say like the lower body is movement, so that type of movement is being classified or detected here. And what you see in this upper like right hand side, this so this is just a spectrogram plot that we are obtaining from this radar. So this person is basically doing very crude movements of the upper body, lower body, and a combined movement of upper and lower body. So and we are detecting that. So what you see is that we have this particular spectrograms from which we apply some sort of intelligent algorithms, machine learning algorithms, and then we detect these uh, like activities. So it seems pretty linear problem, right? So it seems that like what's the big deal in that? You put a radar and you do some experiments and then you classify. But this is before going to this classification problem, this is a data problem, because so what we see is that we need so what we need for the classifiers or the machine learning algorithms to work is data, right? And what we were working on this radar or the electromagnetic data. So we need to have like good quality of data to learn the model, to make our machine learning models learn on the data so that we can perform this activity classification or whatever we wanted to classify in the real life scenario in a like uh, in a very practical way. But what we found is that, so you might, you are, I'm sure, like you are very well versed with the IEEE data port, which has a lot of data available or lot of different types of data, not only biomedical data. There are a lot of different data that are available in the IEEE data port and associated papers also. There is Kaggle, which is also what do I say, playground for the machine learning enthusiasts like us who work with the data and the machine learning algorithms. And then we have also different types of data that are available on different websites. But what we found is that at least at that point of time when we started this research, so there were no data available from the radars or the electromagnetic data on activity or gesture, and forget about the cardiopulmonary activity. So there was no at least mention of any cardiopulmonary data of available anywhere in the internet. So after, so let's say now today if you search, so you might find a few data that are available online, a few data in the like IEEE data port also, but that came a lot later than when we started this work on. So for us, the problem was having a data, like generating data. Now, what was the problem? We have our radars. We can do a lot of experiments in the lab. So then, what's the problem? The problem is, so we have the radars, and the radar um, data that depends upon a lot of different parameters. So let's say. Let's say if I have a fixed distance of the person from the radar. So let's say the radar is placed here and the person is standing here. So let's say I fix the distance at 1 meter or 2 meters, whatever it is. So even if there's a few centimeters of error in the that distance, then also the data that we have, data that we get has a different signature. It varies. So we have these variations in the data. The data also varies depending upon the human, the human's shape and size, and the because depending upon the human shape and size, the RCS of the RCS changes, and depending upon that, this radar signature changes. So then what we thought is that can we build a simulator? So why not build a simulator that can simulate the data, right? So that can simulate the data, and then if we have a lot of simulated data, so that we can help to that we can use as our training data to train a model, any AI or ML model, and which can help us to detect or classify the gestures or the activity. So what we did is that let's say we took just one or two persons like data, or so we just put one person in front of the radar and asked him to do so we have different categories of activities that we wanted to classify, right? So let's say we have 10 different categories of activities that we wanted to classify. So we asked the person to perform those activities standing in front of the radar, and also we have like another sensor which can take the joint coordinates of the person. So what we have is the joint coordinates of the person, and we built this human model and we generated the radar return signal. So based on the joint coordinates, we and our human model, we generated the radar return signals, and these radar return signals, as you see here, so these are the radar return signals. So these are our simulated data. So these are used as our training data to train the ML model. And when the actual radar signature that came from the like actual human doing some activity, standing or sitting in front of that radar, so that is being detected and then classified as different various activities. So I'll just show you a very small clipping of our radar simulator framework from human gestures. We called it RADSIM or radar simulator. So what we used is Microsoft Kinect at that time to get the joint coordinates. So to get these 20 joint coordinates, and then base the ellipsoidal human model that we like that we simulated. So based on these two, we calculate the radar return signals. So you see, I'll just show you here. So this particular picture, this shows the coordinate system. So let's say the person is standing here, and this is the XYZ coordinate. So here, enter the radar location. So based on this coordinate, we have to enter the radar location, because let's say the person is standing here, and if the radar is kept here, the signature will be different when the radar will be kept at another position. Right. So the location of the radar with respect to the human is very important. So we need to take that into consideration when we were building our simulator, right? So first we entered the like radar location coordinates, and then we entered the like subject ID, some gestures that we wanted to perform. So the first gesture was like throwing a ball. So here you see this human model is showing that throwing a ball. So distance of the person from the radar, that we have now fixed as 2.5 meters, right? Now we have just shown a different orientation of the person, and then we use it to calculate the radar return signals. When we click this calculate radar return, so based on these inputs that we have given, our simulator calculates the radar return signal, and what you see is a spectrogram of the radar return signals that has been simulated in our simulator. So in this way we can, or we have simulated like n number of gestures with n number of variations in orientation with respect to the radar, variation in the distance from the radar, variation with the plumpiness of the human. So let's say we have used a very short and plump human model. We have used a very tall human model, tall and thin, and like average sized human model. So we have considered all possible realistic or practical variations that can be possible in a data to generate a lot of different variety of data, so as to get a like accurate, precise and generalized like machine learning model, which could have like then which we trained. So this is this our particular simulator. This we have also patented. So now what we were able to do is we were able to categorize these activities, the physical activities, gesture, fall detection. So rehab progress. So rehab progress is another thing that we wanted to do. So let's say a person, so that can be, so I started this by saying you that we started this work for when this problem came to us for a solution for the elderly people. But it doesn't mean that it will not work for any other people. So it works on any human being, like at any part of the world, right? So let's say a person who has suffered a accident, trauma, or may have suffered a stroke, and so after treatment in the hospital, that person comes to his home, right? And then he is undergoing like physiotherapy, rehabilitation process, and also that person has to the progress of that process has to be monitored from time to time. So when we were able to categorize and track the activity of the person like 24/7, then we were able to able to monitor the rehab progress, and we were able to say that how much like progress he is making, or how he is lacking behind. So that helped the person, or the medical practitioners, or the healthcare providers for them, to help them in a more suitable way to improve their progress. Now, at this next level, my question is, like after me speaking for a little more than half an hour, how are all of you feeling? How are you? So, uh, when we go to a doctor, or when we are not feeling well, then we visit a doctor, right? And so what does the doctor do? The first thing that the doctor do, so either he will just put his or her fingers on your palm and measure your pulse, and uses his stethoscope for some auscultation, or like physical examination, right? So and see, you see, these are the vital parameters. So there are 5 vital parameters: heart rate, blood pressure, oxygen saturation, respiration, and temperature. So um, with now a last couple of days from the last week, again the social media is flooding with the news of a new virus that is, I don't know what the situation is, but that is bringing a lot of memory for us back for the COVID time, right? So these vital parameters are always there. So whenever you see a doctor for a regular checkup, or you or somebody is admitted at the emergency of the hospital, these are the parameters that are first checked, and that gives you an idea of how your health is, or how your inner health is, right? um, Now you see, among them, this heart rate and respiration itself tells a lot about your, so these, among these 5 vital parameters, these two are the most vital, right? So you see, this is how like doctor measures your pulse or heart rate, right? But can you tell me how a doctor or a medical practitioner, or maybe a nurse caregiver, measures your respiration, or how it is done generally, or what is the test that you have to undergo to get the condition of your respiratory system? So let's say, for your heart health, you do ECG, right? You have to either do ECG, echo, or at the very beginning, the doctor gets your pulse, and then maybe ask you to do a ECG or a echo. But like, for respiration, generally what is done, and what is the test that is being asked in most of the cases, or the gold standard? So you see, this particular picture, so this is back from 1900. This is how the first ECG was done. And now you know how far we have come from that point of view, right? So now ECG is a portable device. Even the students are doing a lot of experiments with their own built ECGs, or the ECGs that are available from the like off the shelf in the market. And also, let's say, like a lot of some wearables, like some heart lockets, some smartphones, or some smart watches are also giving us ECGs sometimes. I'm not talking about any reliability, but they are giving, right? But can you tell me like what this person is doing or what this person has been subjected to do? So this is ECG. This is a marker of our heart health, and that is one of the gold standard that the medical fraternity agrees on. Yes, ECG is one of the gold standards for your heart health. Similarly, this is how a spirometry is done, and spirometry is a gold standard for your respiratory system or respiratory health. Okay, so uh, uh, if some of you have undergone spirometry or pulmonary function test that is called as PFT sometimes. So PFT spirometry, like more or less the synonymous terms sometimes used. So if some of you have undergone this or some of you have seen any of your family members or friends to do a spirometry, then you might know how hard this process is to do. So just to measure your heart or lung, respiratory system or lung health, what is used is that, let's say you have to put this particular mouthpiece in your mouth, and sometimes they block your nose or sometimes you don't, but then the person or the patient has to undergo a very complex maneuver to complete this process. So what he has to do, so he has to breathe in and then hold his breath for few seconds and then blow out. Like blow out means blow the whole air out of his lungs. uh, in ideally there should not be any air left in your lungs. You should blow out in that way. So so you see, this is a very hard process that the person has to undergo, and most of the time like hardly people are able to complete it in one go. So even for the normal people means who do not have as such lung or respiratory ailment, even they find it difficult to complete this particular complex maneuver. And this is not recommended for children below 10 years. This is not recommended for, let's say, the patients who have some heart diseases, heart transplants, bypass surgeries, and a lot of different other diseases too. So you see, there are a lot of problems with the current facility. So as we were talking about our previous objective, so that was doing a non-intrusive monitoring, because there the privacy was one of the main concern or one of the main criteria we have to consider. And another another criteria was to do it on a 24/7. Here also we wanted to monitor the heart and the lung health of a person without actually putting a sensor on the body, so that these maneuvers or the complex processes like spirometry like is not needed, and you can just do the monitoring on go. And what COVID has shown us, that the importance of non-contact monitoring, right? So I'm sure you all of us remember that how difficult it was for the medical fraternity, obviously for the whole world and specifically for the medical fraternity, to do their duty every day, where they were coming in contact with the people with the communicable disease, right? So that is their job, and they has to do it. But what if we can assist it with them with some technology which minimizes their contact with the people? So uh, our solution that can be put in a, let's say, a doctor's clinic where the patients are waiting, or in a OPD, or maybe on the top of the bed or the below the bed of a person in the ICU, and without any contact or without any technical intervention, that device or solution can measure these heart and respiration parameters on a 24/7 basis. Now, these were our proposals, right? So we thought, yes, we know about radars, we know about signals or the radio frequency signals, and we know about the heart and the lung, and how their normal range of beating and all. So let's say like the normal range of heartbeat, it lies in a, so like generally people's we have like uh, got from our textbooks that the normal heart rate is 72 beats per minute. But let's say if we consider, if we think about a range, then the normal heart rate like ranges from 60 to 100 beats per minute. So but that varies from person to person, right? So let's say for a person for whom a 60 beats of heart rate is a normal, if that person has suddenly his heart rate has increased up to, let's say, 80 or let's say 80 or 90, even 80 or 90, then that person would feel distress. And let's say for a person whose heart rate is generally around 90s or 100s, if that drops to 70s or 80s, then also that person will have distress, and that person mostly is undergoing some physical or mental trauma or disorder or some like discomfort. So ra so that was another motivation for us to do this particular research. And you know, the respiration rate, if we talk about, the normal respiration rate is generally around, so it varies. So it varies from 10 or like 15 breaths per minute to 25-30 breaths per minute. So like this 10-15 to 25-30 breaths per minute normal. So what I mean by normal is that these are the normal ranges when the person is in a resting state. So it's not that I have come from, I have ran 5 kilometers and I come and then also my heart rate or the respiration is in the same. It is not. But this is a normal resting condition. So this is what we know. So if we convert the heartbeat per minute to frequency, or the respiration breaths per minute to frequency, it comes in these two ranges. For the respiration, this is around zero point 0.1 to zero point 0.7 hertz, and this is the range, normal resting. And for the heartbeat, it is around 0.92 hertz. So you see, these are very, first of all, these two, both of these are sub-hertz frequency ranges, very, very low frequency ranges. And secondly, these are very close frequency ranges, and sometimes these are overlapping. So respiration and the heart signals would overlap. So you get like how close this was in the like technically if we talk about the signal sense. And another thing was that, so what was our problem going into more deeper? So let's say we have we have a radar or a like antenna and a receiver kept in front of a person, and the person is breathing or like is normally sitting. So that means the person's chest wall is going up and down, up and down. So here just from the movement of the chest, we have to detect the uh, condition about the respiration and the heart. So why the chest wall moves up and down? The chest wall moves up and down due to the combined movement of our lungs and the heart. So the heart beats and the lungs expands and then relaxes, expands, relaxes. So uh, due to this lungs and heart, the combined movement of these two, our chest wall moves up and down. And from this chest wall movement, we have to detect. So our radar or our what we are getting from the RF signal. So there is a radar which is transmitting electromagnetic waves. It is reaching the chest wall, which is moving up and down. So the transmitted RF wave is being disturbed by this movement of the up and down movement of the chest wall, and that disturbed RF signal is being reflected back to the receiver. Now, this difference between the transmitted RF signal and the received RF signal gives us an idea about this chest wall movement. And from this one source of chest wall movement, we have to get information about these two different sources. So that is a difficult problem. Now, so we did this research back in 2018-19, that time. So even that time, or even if I talk about today, there are some devices in the market, some RF devices using some radars in microwave or millimeter wave ranges, which they claim to detect your respiration. But till date, there is no device in the market which uses RF to detect both your respiration and heart rate. Like there are some radars or devices like that that might claim to, but actually like they are not foolproof, or they do not work well. So because it is still a difficult problem to solve. So what we did, so our system on the very top, it looked like this. So we had a sensor node. So our total module was the IoT based module. So we had a sensor node, we had a we had some cloud, and we have a remote PC. So what our sensor node, it comprises of, so we use two radars. So we use a multi two channel radar. So one was 10 gigahertz and another was 24 gigahertz radar, microwave signals. So we have a multi frequency radar. We have our own built preamplifier and filtering circuitry for this. And then we have a data accumulation or encoding module. And then we have a MQTT interface. So this MQTT is a very specific protocol for RT, like data transfer, that is message queuing, telemetry, and transport. So using this MQTT interface, so we what we did is that we were able to record the data from the person. We were able to perform the analysis or the analytic part, and then we were able to um, send it to either a remote PC or a remote whatever. So when I say remote PC, it doesn't mean only PC. It can be like your phone, tablet, whatever it is, or some cloud server also. So as because we were creating it as a solution to be deployed somewhere, so we had different sort of flexibility that we devised in our system, right? So when I am talking about flexibility or application flexibility, that the user can choose based upon their need, is that, let's say, so uh, uh, if the user want, the whole data analytics can be performed in this sensor node itself. Else, the one thing is the whole analytics can be performed here. And let's say we are finally calculating your heart rate and respiration rate. So after doing the complete analytics, we can only send the data about the respiration rate and the heart rate to the remote PC or the server. Else, we can directly send the raw data, or the preamplified filter data, radar data, to the remote PC or the cloud, uh, which will do the analytics there. So whatever was suitable for the user, they can choose that. And we use the MQTT. There are different types of protocols, right? There are different types of ways in which we can this transfer this data. So we were using Wi-Fi. That was one reason. Another reason was that one of our main thing that we have to keep in mind was that the low latency and real time. So 24, so long term monitoring, 24/7 monitoring, low latency, and there should not be any data drop. There should not be any so when we were accumulating or the data acquisition, there should not be any data mismatch, data drop. So all these things keeping in mind, MQTT was one of the most suitable things that we could have done. So we took MQTT. So going into more details of the how we have done. So we have this two channel of data. So let me go back. So I mentioned that we have radars, multi-frequency radar. One radar was 10 gigahertz, another was 24 gigahertz. So let's say, so we are calling it channel. So this is channel 1 and channel 2. So the data is coming from channel 1 and channel 2. We do pre-processing. That pre-processing consists of like uh, a software level filtering, signal detrending, signal denoising, checking whether the signal quality, all this comes under pre-processing. And then we detect the presence. Presence means we are detecting based on the signal energy level. Heuristically, we have found out a threshold on which of each channel on which we if the signal energy from each channel is within a range, and if it then we take the signal, otherwise we discard it. So in that way we detect whether a person is present or not, and we also detect the signal quality, uh, like each time we are doing the whole analysis, we need to check the signal quality. So if these are like passed, and then we go for detecting the breathing rate and the heart rate. The BR is the breathing rate and HR is the heart rate. So okay, one thing I forgot to mention is, so let's say we are doing a continuous monitoring, right? So we are monitoring for long hours, or maybe 24/7, 24/7 in most of the time. So but so how much data, or what is the time window that we need to take to do this processing? So we need real time, right? So we needed the data. So we do this analysis on the chunk of the data that should be very small in time. So let's say it would have best if we have done it if like every second or so, but that is not a like practical or feasible one. So we what we were doing, we were taking data of every 15 seconds. So we, whatever the data was coming through these two channels, the channel 1 and channel 2, we were windowing it using some specific windowing functions, and then we were windowing it for a duration of 15 seconds uh, with some overlap. So with every 15 seconds we are doing this whole analysis. uh, Now you might ask you, why 15 seconds? 15 seconds because the heart rate is faster than the breathing rate, right? So the breathing rate is slower. So the one breathing cycle, it takes at least at least 3 seconds to complete. So if we took so we cannot take so if we took 5 seconds, then it might happen that we might get one complete cycle of respiration, or we might not get one complete cycle of respiration in a 5 second window. So, but we needed at least two full cycles of respiration, uh, or like at least one, better if we have two full cycles of respiration. So, to ensure this criteria, we took a 15-second window. So, for each 15, so whatever you see here in this pipeline, that is done for every 15 seconds. So, once a presence is detected and the signal quality, so presence is detected, then we do a breathing and the heart rate detection. So initially a band pass filter is a band pass filter with the range of like 0.2 to 2 hertz is done. So 0.2 to 2 hertz, this comprises both the breathing and the heart rate. So the heart rate was from, let's say, zero point 0.9 or 1 hertz to 2 hertz, and the breathing is from, let's say, zero point 0.3 to zero point 0.7 or zero point 0.8 hertz. So these are the range of the breathing and the heart rate signal. So to comprise all of that in that band, so we did a band pass filter. After that, we did signal quality check based on the based on the autocorrelation or the area of the autocorrelation function. So we did autocorrelation of the signal, and then we found out the area under the autocorrelation, and then we heuristically defined what should be the range of that. Now, why autocorrelation? Now, see, this uh, so our heartbeat, our respiration, all these are periodic signals, right? So these are not some random signals or some periodic or non-stationary signal. These are periodic signals. So if we have a periodic signal, then the autocorrelation, if the autocorrelation is higher, that means that that periodicity has been is intact in the signal that we are acquiring. So that is why autocorrelation was one of the like tools that we have used here. After that, when the signal quality check has been done here, then we do like when we have two different blocks, one for detecting the breathing rate and another for detecting the heart rate. Then we have again two different bandpass filters, and then we do optimal channel selection, FFT, and then finally get a breathing and a heart rate. So what this enabled us is that from this particular analytics, you can see that we are simultaneously detecting the heart rate and the breathing rate, and this is real time. Now you might argue that we are doing, so what we are doing, so we are taking this 15 seconds with the window with some overlap. So almost every 10 seconds, at least, even if we take 15 seconds with 0% overlap, then also every 15 seconds we are able to give you a value for your breathing rate and the heart rate. Okay. And if you see, this complete process is data driven and calibration free, so you do not need to do any calibration on the device or the system. So you put the radar, and whatever the calibration or the signal quality check, the presence detection is required, that will be handled by the algorithm itself. So I'll just show you a very small video. So this is one. So this is my colleague Smriti. She's sitting in front of our very first crude version of our solution. This is the radar module. So this white screen that you see, this is the portable display that we have. So this is done at a distance of 1.5 meter. But at this distance, the standoff distance from the radar from which we can measure, that can vary. There are some radars which can even measure from a distance of like more than 10 or some 10 meters or so. So I'll just play a small video. So this person is just sitting at rest, and so just she's sitting. So we have our module, and this display is showing us the data from the two radars channels. So I'll just pause and I'll just show you one thing. So this is radar 1 and radar 2. So I was telling you about, so we have one 10 gigahertz and one 24 gigahertz. So these are the two different plots that we are getting. So whatever signal you see here, this is the raw signal, the noisy raw signal without any sort of filtering. So that we get. And here what you see here is it is giving you two values, one for the breathing rate and another for the heart rate, right? And it will also show here a cross or some notification will come when the person is not here. So that means when the presence is not detected. So sometimes the cross comes here, that means at that particular time it is not calculating the breathing or the heart rate for that particular window, um, because the signal quality check has not passed, and then it will again start collecting when in the next 15-second window the signal quality check passes. So now we have a modular solution. This solution can be scalable across various users and use cases. We have a flexible and open hardware ecosystem. So what you see, so we have two different radars, so that we have used. Now, if you ask that what if we do not use that particular radar, so make and like company manufacturer of that particular radar, and we go to some other. No problem. We just have to do a little bit customization of the hardware and initial pre-processing. The rest of the algorithm will work as it is, because the logically this thing works. The solution is completely frugal, uh, uh, low cost. Yes, low cost with respect to the other sensing that are available, but I won't say cheap. So yes, it is cost effective, and it extends flexibility to physicians. Now, what you see here is like filtered version of the breathing signal. So here you see this is a slow breathing signal. This is a normal breathing signal. So you see the window here for all of these three graphs is a 12-second window. For this 12-second window, in the slow, the number of breathing cycles are less. For the normal breathing, there are more cycle, and in the fast breathing, there are obviously much more compared to this slow and normal breathing. So we did we to acquired a lot of data of participants from inside our lab, outside our lab. We did a POC at some of our collaborated hospitals in India and also outside. So finally, like what we got is an error of 1.47 breaths per minute. So I'll come to the significance of this error or what we are looking for and not. And for the heart rate, so let's say we all know the PPG, right? So the device that you put on your finger, like we all know due to COVID. So the device we put on your finger. So this is the blue line is the heart rate that has been recorded using that PPG device. The red line is using our radar, and you see like this is almost overlapping. Yes, there are some instances where our radar has skipped or missed some bits. Uh, Obviously, so there are some other differences between, so the PPG is measuring the heartbeat at your finger, and the our radar is measuring the heartbeat from your like chest wall movement. So there are some delays also. Again, the accuracy here was 92%, but so these are some slow and some like normal heart beats, so from two different peoples also. So you see these are more or less overlapping what we are seeing. This also we have patented, but what I want to mention one thing here is that so uh, when we were doing this particular research or or any of our work that we do for human sensing or imaging, our idea or our objective is not to replace a existing gold standard device or technique. For example, I'm not looking for a device which can measure the heartbeats and can replace ECG or PPG. No, they are there. That is fine. But we are looking for a solution that can augment or can act as a pre-screening, or you can take it at home and put it there and do a lot of different things that you cannot do with ECG or the existing techniques that are available. So this is one thing. Secondly, when I am measuring the cardiopulmonary signals or cardiopulmonary signatures of people, like on a 24/7 or a long-term monitoring purpose, then it is not important to get the exact number. Let's say if I measure by ECG, my heartbeat comes around, let's say, 70 beats per minute. But let's say when I measure by our radar, it either comes to 65 or it comes to 72, 73. So, uh, so then also it's okay. Our idea is to get a trend or trend of my or a person that I'm recording, to get a trend of its own signature on a normal basis. So I have a normal signature, right? So there are variations. I have a variation of my heart and breath signature throughout the day, depending upon the physical or the mental workload that I'm going through, right? But there's a trend. So anything when these signatures go out of the trend of that particular person, then we put an alarm. We raise alarm. We give notifications. Our system like pushes notifications to the caregivers or the hospitals or the person concerned person. So here the idea is to get a idea of like trend, the deviation from the normal, or like the trend that we are getting. So now detecting the cardiopulmonary activity, we are able to get monitoring vitals, respiratory system. So we are from this we are also able to like pre-screen diseases, get an assessment of the cognitive status, and obviously monitor 24/7 of daily life activities. So this is the Shine Senior facility on which we have done a pilot study on. Uh, and let's say our this particular solution has been like offered to a lot of other different applications also. So you see, there's a term called like geofencing. There in the large inside factories or like warehouses, there are very big different machineries or instruments which can be very harmful if a person crosses a certain limit of going in front or of that machine. So that is called geofencing. So our this particular solution is proposed as geofencing to these large workspaces and also to monitor the safety of the workers there, on which again we cannot put sensors on. Like for example, inside mines, inside blast furnaces, this type of scenarios. And obviously, as we belong from the Tata Group, we do care about our societal impact, and yes, it actually is capable of, and with our pilot study being deployed at certain spaces or places, we were at least able to assist the doctors or the healthcare providers in managing their time and effort to at least some extent, so that they can cater to a lot of more number of patients, right? And another thing is that pre like previously the idea was to have so we used to go to doctor previously when we feel ill, right? But today, nowadays, we are more looking forward to our general wellness. So in that term also, this life signs monitoring or vital sign monitoring, this gives an idea of our overall wellness and how self health tracking also. So I'll just in last few moments I'll show you some clippings or some of some related work. So we did. So let's say here is another radar. So this is a person standing. So this is able to. This is used for people tracking, right? So this is able to detect a person who is moving, how the person is moving, in what direction he is moving, and also the speed of movement. So now, this is one of the example of how it is used for people tracking. So, and you see, these are the signatures or the velocity versus time signatures that we have obtained using the radars for different types of activities. So this is, let's say, this is for walking. This is simulated frontal fall. So we have simulated frontal fall. So we simulated that we are standing and then just we fell down. So what if this happens? So just to detect the fall detection, to facilitate the fall detection, and to in all of the signatures, it is very visually, it is very well differentiated. It can be differentiated. Like you see, there's this difference with the standing up and sitting down. The standing up, it goes here, goes up, and then almost here. And the sitting down, it is just the opposite signature. So um, even from these very crude velocity versus time plots, we are able to see that we can differentiate these activities. So it ultimately enabled us in detecting or so I'll just show you. So we used different types of radar. So what I was talking till now, we used continuous wave radars. This is a demo with target distance and velocity estimation using a FMCW radar, or a frequency modulated continuous wave radar. So here you'll see that the person is moving. So I'll just so you just look at this person, and the radar is here. The person is either moving towards the radar or back, away from the radar. And here in this particular screen, you see this green dot, which shows the footprint of that person. So I'll just play. As the person moves, the this footprint also moves, and this is showing the distance and the velocity. So here the radar was there, the person is moving, right? So this is the person, this is the wall, the distance, the velocity, right? The person is standing still. So it is also still. And again, the person is moving towards the radar. This footprint is also moving towards the radar. So this is a very crude lab level demonstration of about our pickle tracking. And also it is, here you will see like we are able to detect when the velocity changes or the increases or decreases, right? So we have done one of the POC with one of our clients on a human proximity sensing for vaccine clean room operations. So in the clean rooms, what you need, there are some devices, there are some facilities which need very precise, we need to follow like extreme stringent processes or procedures inside clean rooms, that where the person should be, should not be, should so we did a proximity sensing based on ultrawide band tags, and we have done this POC for one of our pharma companies for their vaccine clean rooms. Then we did a activity tracking for human being and the worker safety, that I have already told you. So these are the spectrogram signals that you see. So here, let's say the person is standing, it is bending up, then again he is bending down and then straight and then standing. So there's this difference. So we did a lot of analysis on the signature itself that we are getting from the radar. So our main idea, so yes, the AI or the ML algorithms are there to assist us, for us or for our group at least. The AI or the ML algorithms are the tools that we use for our solutions. But our main concern is, or our main objective is, to look into the physics of these signatures or the sensor signals that we are getting, signals or the images that we are obtaining, and then find out the parameters which are able to give you a better definition of the targeted motions or the activities that we are trying to monitor or detect. So, in very short, this life science sensing, this can be the applications are innumerous. So, even under, I forgot to mention, so one of the very plus points of the radar was, like, they can penetrate objects, right. So they can penetrate materials, see any materials without the metal. So if I place a radar in this room, even I can monitor a person who is in the other room. So through wall monitoring is also possible. So if you can see my video, so there was a proposal that was floated by DARPA, the Defense Organization or Research Group of US. So the problem was, so let's say you have a wall and there is some person behind the wall, and you have to just detect whether the person is just standing like this or standing with a gun in his hand. So just from his gesture or from the signature of the body, without going inside, we have, like, they wanted to detect whether they have a gun or not. So these type of applications for primary healthcare centers, for sleep study, for and very specifically for, let's say, for infant monitoring or neonatal monitoring. So a lot of times inside NICU or the neonatal ICU, the babies, the very small babies, they have to put through the sensors on their bodies just to monitor their health, and that is very, very painful for them. So what we propose is that the our solution is capable of doing exactly the same without causing any harm. One question that arises always when we talk about these solution, the RF based, is the safety, or how safe it is. So uh, without going into the technical details of the safety, in one line I can mention, or I would definitely like to mention, is that so we all have a smartphone or a cell phone, right? So they also emit radiations. So the radiation that is emitted by the radars that we are using is 1/1000th time the radiation that is being radiated by your smartphones. So the safety wise, this goes like this. So I'm just at the end of my time. So I'll just quickly. So now what we are doing is we are moving forward. We are working on in-body imaging using microwave and millimeter wave. And so that for early detection of improved patient outcomes. So what we are trying to do is, so we are trying to get the accessible diagnostic beyond hospital. So our idea is that, let's say, for doing a lot of tests like X-ray, CT, MRI, you have to go to the emergency rooms only to perform these experiments. So what if we can come up with a solution for you, so that at least you can do it at your home, or at least at the like doctor's clinic, without going to the emergency rooms. So for example, most of us nowadays have a BP machine at our home. So we always use that automated BP machine. Yes, they are not as accurate as the sphygmomanometer that are used by the doctors, but they at least give you an idea of how are you. So that is good enough for us right now. So in the similar way, what we can bring the medical imaging at like what we if we can make the medical imaging accessible to your homes and at clinics outside hospitals. So that is what we are working on right now. And now with this, I end my talk. Thank you, everyone. And if you have any questions, I'd be most happy to take it and answer them.
Hello, Dr. Anisha.
Hello, Dr. Shah.
Yes. Uh, I must say it is a wonderful, insightful session. So as we draw this insightful session to close, I would ask our audience, our participants, if they have any queries. Because it is my privilege actually to express our heartfelt gratitude to you, Dr. Anwesha, because your expertise and the depth of knowledge you have shared with us today have been truly enlightening. Because this session explored the integration of AI and wearable technologies to monitor the health parameters seamlessly and non-invasively. You actually emphasized also the importance of developing the user-friendly health monitoring systems that can provide the real-time data without interfering the daily activities as well, thereby enhancing the patient care and proactive health management, I can say. So you have discussed also the challenges, related to collecting radar data that depends on various parameters. Also, you also discussed the techniques to detect heart rate and breathing rate using the radar module, even the use on babies. So on behalf of everyone here, I extend our deepest thanks for your time, effort, and the invaluable insights you have provided. So, in my opinion, this engaging discussions and thought-provoking ideas you have presented today here will undoubtedly leave a lasting impact on all of us. So, on this note, I would again ask our dear participants to raise any kind of questions, because it is a wonderful opportunity to have Dr. Anisha with us, so that we can raise our concerns with in such a manner, such a beautiful manner, and such a wonderful platform.
Thank you, Dr. Shah. Thank you. Thanks a lot for having me. I hope like I did not make the participants sleep. So thank you.
Okay, so I just take 1 or 2 minutes from you, Dr. Anisha, because I want to request all my participants to just put on the camera so that I can take the, a screen share, a screenshot of the attendance. So participants, please put on your camera for 1 or 2 minutes, please. Thank you so much. Thank you so much. And dear
Thank you.
participants, you can put off your camera. And this is the last session of today's. And we have shared some useful and very important notes to your WhatsApp chats as well as an email for the attendance and the participation. Please go through this. And we have also shared the FDP schedule also for our 6 days, among which 2 days have already passed, and we have remaining 4 days. And in the last day, actually, we have some valedictory session as well as the online test schedule. And the feedback forms of these 2 sessions are going to be distributed in your Gmail account in very shortly. Thank you so much and have a good night.
Hello, madam.
Yes, yes.
Madam, whatever PDF file you have shared, it's not opening.
Okay, that is the FDP schedule. So I'm going to share the.
I think, madam.
Okay, okay,
As
sir.
you have disabled the commenting, I tried to give a question mark there, but now that also not possible.
Okay, sir.
I cannot
Then
communicate over WhatsApp.
okay, sir. Then just give me 1 or 2 minutes. I'm going to share the JPEG
I think you
format.
have just shared the link, madam. You have to share that particular file. Then
Okay,
only it will be
okay.
visible.
Thank you so much. Thank you so much for this kind feedback, sir. I'm just going to share you
Otherwise,
the
like we will
image
have to
file
register
also.
in the Adobe. It's a long process. We
No,
have to
no, no,
register in
no.
the Adobe, generate
No,
user
no,
ID
not.
password, then only I can access the file.
No need to do this, sir. Just give me 1 or 2 minutes so that I can share the image file as well. Okay, sir?
And madam, I have a suggestion. I think it will be
Yes.
better if you can open a Google Classroom where you can upload all the study material. That will be better. Because at the end of
Okay.
in the 11th this one hour, especially on
Yes.
the 6th day, if we get all the notes, it will be difficult for us to go through all the parameters and answer the questions. Because I have already attended
Yes.
previously also AICTE FDPs, and they are like the questions are quite tricky. So I think it will be better like every day at the end of the session, if you study at least for 1 to 2 hours, we can do well in the assessment part. Thank you very much.
Okay, okay. Thank you for this kind and valuable suggestion, sir. I will surely think about it and I will contact to our resource person so that they can give us the resource material so that we can, proceed in that way. Thank you so much. Thank you so much for this
Hello, madam. I
suggestion.
have one more suggestion.
Yes.
There are situations when they are not ready to like share the PPTs also. It may be possible. So because there's a matter of privacy and intellectual property right.
It may
So in
be, it
that
may
case,
be.
if any related paper is there, research
Sure,
paper,
sure.
that can be uploaded in the Google Classroom. That will help us a lot. Thank you.
Absolutely, sir. I will communicate to each of the resource persons to, just give us the link or share the paper so that from where actually they are going to, give the this online presentation and sharing the knowledge so that we can be, very much aware of what kind of, things they are going to deliver within this short span of time. We will surely do this, sir. Thank you so much. Thank you so much for this valuable suggestion.
Thank you, madam, for the excellent sessions. Thank you.
Thank you so much. You're welcome, and all the dear participants. So today we are going to close our session, and so tomorrow again from 6 p.m. you are going to have the session. I will also share the feedback forms and also the image format of the FDP schedule so that everybody can access the FDP schedule. And in the mail also, Sir Deep Sir, I'm talking to you. Actually, if you could just after closing this session, if you go through your mail, then also you can find the FDP schedule in the PDF format as well as in the image format also. I have already shared that one also. And I'm just requesting all the participants to, if anyone of you cannot find any kind of mail from us in your normal inbox, then please go and check your spam folder. Sometimes some of the participants have already, given us the feedback that yes, ma'am, we have not received any kind of joining a meeting link or something like that. Whenever I have replied that I have sent that particular link in the registered email ID, then they have again checked and found it in the spam folder. So that is one feedback I have received from some participants. That is why I thought it is better to share with you that if you cannot find this in your normal inbox folder, please find it and go and check it once in the spam folder. Thank you so much. So I'm closing the session. Thank you.